Okay, so I'd also like to join the other speakers by thanking AutoCube for putting this together. I think maybe we should have a vote on whether this should happen every year or every couple of years, but I think generally it's a fantastic meeting. The only problem for me is it's too close to my lab, which means I still have to teach and go back and forth to the lab. What I'd like to do today is to talk about, picked a couple of experiments we've been doing in the last 2 or 3 years, focusing on developing ways to, let's say, take fully encapsulated heterostructures and also monolayers and tether them to very high Q optical resonators. And typically the traditional ways that people have developed high Q single mode cavities is we've made photonic crystals where you punch holes in a material. Of course, with 2D materials, you want to avoid etched surfaces, you want to avoid etched holes, and you'd like to figure out ways to get high Q and also maintain the pristine excitonic photophysics of the materials. And this kind of blurry image in the background, I'm going to show you in a second, if I have a pointer, I'm going to show you in a second some slightly less blurry images of the same thing. It represents a silicon nitride photonic crystal cavity. If I zoom into the middle of one of these nanobeams here, we actually have a heterostructure which is clad by boron nitride on both sides. And the thickness of the boron nitride actually allows us to pull the optical mode into the 2D material and not have it penetrating very much into the underlying photonic crystal. So the photonic crystal kind of is there just to provide some optical confinement and create in the middle of this thing 2D heterostructures, as you see in this SEM image, which are placed on top of these nanocavities. And obviously the first thing we thought about when we made this type of structure, we were interested in creating defects in these cavities, coupling defects to high Q modes, doing cavity QED experiments. So in one way, you have this very interesting interaction between photons and excitons. And actually it turns out that, maybe I use the other pointer, it turns out that the cavity Q can be 10 to the 4, 10 to the 5 in these types of cavities. And the cavity exciton photophysics you expect is there to see. But in 2D materials, there's a whole bunch of other things which are there to see as well. So not only does the exciton couple to the photonic environment and to the single mode of the photonic cavity, it turns out it also couples very strongly to vibrational modes, both phonons in the 2D material, also mechanical modes of the freestanding nanobeam cavity. And in this way, the excitons in these types of systems, they mediate coupling between photons and phonons in the system. And because of shortness of time, I'm only going to talk about the photons today, but I'll put some references up in case you want to talk to me afterwards about the phononic part of the story. The most important slide, I thought I'd start with this because traditionally I went out of time, is to thank the people who really did the work. So in Munich, the 2D people are Andreas Stier, Nathan Wilson, Pedro Subele, who are group leaders and postdocs in the group. Viviana is also one of the postdocs. But most of the work today I'll present has been done by Chenjiang Xian, who was a postdoc who's recently taken up a professorship in Beijing. And I'd also like to thank Alex Hohleitner and his group. We did some of the experiments I'll show today in collaboration with his group. Okay, so the structures that we've been realizing, basically we start with low-pressure silicon nitride layers. These low-pressure silicon nitride layers are not very luminescent, so you can do low noise, low background measurements. And the first thing we do is we pattern on the surface a one-dimensional grating by patterning the silicon nitride, etching down, and creating essentially what is a 1D grating along this X direction. Now what we do then is we borrow very old ideas. So this is the paper from Noda's group from more than 20 years ago, where if you chirp the period of the grating, and if you do that according to a Gaussian envelope, so we slowly make the periodicity smaller and then larger again, varying it by about 5%, you can localize a single optical mode over about a wavelength and a half in the middle of this cavity, and this mode can have very high Q because this type of tailoring prevents radiation loss into free space modes. So you make the Q high by suppressing radiation from the cavity, which is bad for the experimentalist. It means you don't have much signal, but you have to be careful about how you collect the photons from these things. If you look at the sample in an optical microscope, at that point it looks like this. So this is the direction where we have our 1D grating. The apparent color comes from the grating. If you zoom in and look at it, you see This is 20 nanometers, so the sidewalls of this grating are really beautiful. The nanofabrication is the hard part of doing this. And after we have such a structure, we take a pre-prepared heterostructure, and by viscoelastic stamping, we just place it on top of this grating so that we cover the region in the middle of these waveguides, of these gratings where this chirped region is. We then cut up the thing into a series of nanobeams. There you see them in an optical microscope image. It doesn't look so nice, and that's because of the contrast, because of the silicon substrate, and then we remove the silicon substrate as a last step, and then you get very, very beautiful nanobeam cavities. Each one of these has a width which varies from about 300 to about 400 nanometers. That tunes the frequency of the cavity. And the 2D material, as you see in the background here, the heterostructure more or less covers the entire of this thing. So we have about 20 cavities to play with when we've made this type of thing. There's the picture of it. There's the tuning of the width. There's actually many things I could talk to you about these cavities in terms of their design. I just want to show you a few pretty pictures. So that's a region of the silicon nitride nanobeam where we don't have the 2D material. If you then look at a region at the edge of the 2D heterostructure, you really can see the 2D heterostructure completely covers the nanobeam. And if you look at a region close to where the defect cavity is, you really see nicely the 2D heterostructure spanning over this nanobeam in the width. Maybe an interesting point for the exciton aficionados is that, interestingly, if you control the thickness of the boron nitride on both sides of the monolayer you're interested in, you can actually control the components of the electric field in different spatial directions. For example, if you're interested in dark excitons, you can place the monolayer at a region where it couples mostly to Z-polarized electric field components. So this is actually quite a useful tool to couple to particular excitonic states. Now, when we do spectroscopy on these things, they don't look as nice as some of the spectra that Bernard has just shown you. So this is a typical spectrum with the laser positioned on the nanocavity itself. You see the neutral exciton, you see the trion, the singlet and triplet part of the trions. The line widths here are not great. They're about 5 millielectron volts, so they're not the best samples we've made in the group, but they're fairly reasonable. And if you look to lower energy in this particular sample, you see these very, very sharp modes. These are the nanocavity modes. I'll show you in a second. The Q goes typically for molybdenum disulfide up to about 10 to the 4. And for boron nitride cavities, we actually have Qs which go all the way up to about 100,000 or so. You also see in this spectrum a lot of defect-related emission. This is related to the etched edges of the nanobeam cavity. This is somehow unavoidable. But what I'm going to be showing you is that most of the work we're doing, we're tuning a cavity mode close to one of the trion transitions and using the cavity mode to actually probe the photophysics of the light matter coupling. So these modes, what do they look like? Well, if I look at M1, you see that it's localized over something like 1.5 micron region in the middle of the nanobeam cavity. Putting our laser spot right there, we can tune the mode frequency by moving from one cavity to the next, just by tuning the width. And we can by doing that, we can control the detuning of the cavity mode relative to the trion. And actually, what we started to do was to try to look for strong coupling and such effects. It turns out if you tune the mode into the trion, it completely quenches because the residual absorption becomes so large. You really see as you move in, it broadens and quenches. So what we typically do is we park the mode detuned on the red side of the trion and probe then what's going on in the system. In terms of the modes we see, there's the simulation with FDTD simulations. This is the measurements as a function of nanobeam width, so good agreement. As always is the case for these systems, the calculated Q is about 100,000. For this particular set of samples, the measured Q goes up to about 30,000, 40,000. And actually, if you look at some of the best samples, this is actually just reflecting a single frequency laser from the cavity, and the line width can go down to 20 picometers or so. This is kind of best case scenario. So the 10 to the 4, 10 to the 5 is a typical number we can get with these types of cavities. So Q factors are in the range 10 to the 4, 10 to the 5. And most importantly, this is a fully encapsulated monolayer where there's no holes punched in the system. So excitons which are excited, as Bernard just showed, can diffuse along the axis of the nanobeam cavity. So this is the first thing we started looking at. We were looking at, let's say, light matter coupling in these systems. This is this first paper. And I want to tell you about what happens when the excitons move and when they start to move over length scales comparable to half of the optical wavelength in the system, so 100 nanometer or so length scales. What happens, of course, is that they can move during their lifetime, and they can sample regions of the cavity field which have different local amplitudes, unlike quantum dot cavity QED experiments where the dot is fixed and it only samples a local field at one position. If you're interested in phonons, then take a look at this green paper here. I won't talk about it, but I can chat to you afterwards if you're interested. So this was the idea. The idea was typically when you have light-matter coupling in these systems, we have our excitonic system, and typically we treat this in the dipole approximation. So the typical size of the wave function is of the order of the Bohr radius for a stationary exciton, and that means typically we're in the limit that k dot r is much, much less than 1, and we can adopt the dipole approximation for the light-matter coupling. But of course, in reality, when we create a gas of excitons, they have a certain center of mass motion, and the center of mass motion modifies the excitonic wave function. So this is the center of mass and the internal motion. And because of that, what happens is when you typically compare these length scales, one's about 100 nanometer for the optical field. The other one, let's say, depends on the length, the coherence length of which the, let's say, motional wave packet is moving. And in the dipole approximation, of course, we normally take the field out of this kind of integral, and we say, okay, the local field where the emitter is determines the cavity coupling to that particular exciton. This is something we can't do when the exciton is moving over a significant length scale within these 1D cavities. So this is a problem which goes back quite a long time. Peter Lodal's group already looked at this, well, maybe more than 10 years ago. It turns out when you change the size of the confinement potential, or you use, for example, magnetic fields to change the diameter of the exciton, what you expect is to start off, you follow the dipole approximation, and for very large spatial extents of the exciton wave function, the coupling vanishes, it becomes 0, because essentially your wave function extends over a length scale of the optical field within the cavity. So how do we tune in our experiment the spatial extent of the wave function? Of course, it's not easy. The way we've been doing it is just by tuning the temperature. It tunes the coherence length scale. It also tunes the diffusion length of the carriers of the excitons in the system. So we vary the lattice temperature and look at what happens in the system. This is kind of giving you an idea of how we do analysis. It's a very simplified model. It's certainly not, let's say, correct in all of its facets, but it gives you a good, let's say, qualitative understanding of what's going on. So what we do is we detune essentially the cavity mode from the exciton. We park the cavity on the low energy side of the exciton to prevent spoiling. Of course, there's then some coupling into polaritons, which are either in the strong or the weak coupling regime, depending on the line width, the detunings, and the strength of the cavity coupling. In that case, of course, the two polaritons are defined by these complex frequencies, and strong coupling, of course, requires that G is larger than the difference of the frequencies. If you take this expression and you put it into the weak coupling regime, then what you get is another expression which you can forget instantly, but the one thing I'd like you not to forget is that the strength of the coupling to the cavity is determined by the line width of the cavity mode. So you kind of park the cavity mode below the exciton, and you measure how its line width changes as the temperature is tuned, taking into account all other features like detunings and things. So to give you an idea, there's a typical example. We've done many of these experiments. We park the cavity mode there, vary the temperature. You see the luminescence is quenching. If you increase the temperature, there's also strange things going on with the cavity mode. I'll come back to it. And we monitor the line width of the cavity mode to get a handle of G, and we obtain G as a function of lattice temperature for a bunch of different cavities and look what's going on. What this does is it defines the spatial extent of the wave function. Of course, this should be the coherence length, if you like, of the exciton in the system. And actually, Alexei Chernikov's group have been looking at these types of problems by doing diffusion experiments like the ones that Bernard showed recently in the last talk. And actually, you can get an idea of what the diffusive exciton photophysics looks like. Let me show you a typical example. So this is the coupling strength to the cavity as a function. This is a gas of excitons. It's not a single exciton. And you see here as a function of inverse temperature. And the coupling always shows this characteristic dip and then increase again. So we have a characteristic dip. The point where we have this dip depends on which cavity we look at, but the dip is always there. And the interpretation of this is that as you raise the temperature, the coherence length gets lower. So that basically corresponds to the impact of phonons and other scattering processes. And what you do is you go from a situation where spatial extent is of the order or larger than the optical wavelength to one where it's much smaller than, and that gives you this kind of collapse of the coupling here. We fitted that with a bunch of different models. This is the simplest model, which essentially just has an inverse temperature dependence of the size of the wave function. And that gives rise to qualitative agreement. I'd like to emphasize this is not an absolute fit here. This is actually just a qualitative indication. We can't really extract anything from this fit, just to show the phenomenology we're looking for is really there in the experiment. And if we just take 3 points either side of this is what our referee was beating us up about. And if you look at it at 15 Kelvin, you've got a 43 Kelvin, the line width is narrower. You've got a 95 Kelvin, it broadens, so you really see this dip, which is beyond the experimental error. So we think this is an observation of, let's say, non-local coupling due to the mobile nature of the excitons, and we're currently trying to do diffusion measurements to kind of like back up some of this with quantitative measurements of the diffusion lengths. Moving on, we've also done in the last year or two experiments of the same type, same kinds of cavities, but this time using, let's say, interlayer excitons in molybdenum diselenide, tungsten diselenide cavities. The details are shown in this paper here. Let me just quickly give you a quick flavor. Why would you want to do this? Well, people have 10 years ago already presented lasing in such systems. It's been quite controversially discussed, the origin of this lasing when, say, 2D materials have been tethered to 2D photonic crystals. In the last few years, there's been a number of demonstrations of excitonic lasing using interlayer excitons. And you might ask, why do you want to do that with excitons which have low oscillator strength? Well, there's a number of reasons. Of course, you have an electrically tunable gain spectrum via the dipole shift. You have essentially the Moiré system, quantum dot-like trapping potentials in the Moiré lattice, which are much stronger than KBT. You have interactions between excitons, which gives you an intrinsic nonlinearity operating at the few particle limit. And you also, of course, have long radiative lifetimes, which can either be an advantage or a disadvantage. The advantage is you get high population very quickly because the excitons live a long time. Let me just, because of the interest of time, I can't show you all the details, but let me just quickly show you a couple of examples. That's the sample. I just flick these things and I just tell you what they all mean. So there you see typical luminescence with strong pumping, 50 microwatts. We see the cavity modes, they're now tuned to the interlayer excitons. If we look at much lower power, so that's not 50 microwatts, that's 70 nanowatts, you see trapped excitons, Moiré excitons in this system. If you look at the negative circular dichroism, you pump sigma plus, you see predominantly sigma minus luminescence. That's a signature of R-type stacking. This is, I didn't mention, it's stacked almost at 0 degrees, but it's actually stacked at about 2 degrees to prevent stronger surface reconstruction. And most importantly, if we look at the Zeeman splitting, as we go into the Zeeman splitting, the G factor is 6.8, so that confirms that we really have R-type stacking in this bilayer. And we can tune using the magnetic field the frequency of a single Moiré exciton in and out of resonance with the cavity mode. And this is indeed the experiment that we've done. There's data. It actually looks way better on my screen here than it does on the screen you're seeing over there, but you can see the interlayer exciton. You also see the cavity mode when it's detuned, and we can control with the magnetic field the detuning of the interlayer exciton from the cavity mode. In this case, the Q is only about 10,000 or so. And what's shown in this panel here is the line width of the cavity mode as a function of the magnetic field. And what you should see is that as it comes into resonance with the cavity mode, the line width suddenly becomes much larger, so you have a broadening of the line, and you can use that to fit using a detuning-dependent Jaynes-Cummings model, and if you do that, that would be the fit that you get, this gray line, and the coupling strength for a single exciton would be about 78 micro eV, which is about what you see for optically active quantum dots. It's a reasonable number. We can then, for the same type of structure, we can, let's say, do a kind of Jaynes-Cummings kind of simulation. We can measure the cavity line width. From that, try to estimate what G is. That's what's been done in that panel right there. And the best fit, which is shown here, is for a 78 micro eV. We wanted to confirm that in the next experiment. I should probably finish. Then if you look at, let's say, pump-dependent data, we started by detuning by a long way. So working up here, you see mostly a linear input-output characteristic and then heating at very, very high pump levels. Here you see at 7 Tesla, the line width doesn't do anything, it just stays constant. And if you then come into resonance, you slowly detune and come close to the resonance. and you get to the resonance, you start to see fingerprints of nonlinearities and line narrowings as you pump harder and you populate the system more strongly. So this is evidence that we have inducing, let's say, a nonlinearity in the cavity as we pump harder. I'm out of time, so I won't just speed through the last slide. I'll just click it over and just tell you that we did some master equation simulations which give the same number for the for the exciton cavity coupling. So the equations, the simulations produce a pretty good fit to the experimental data for the line narrowing and for the intensity. This would suggest a coupling of 82 micro EV, 78 was what we measured, so it's kind of in reasonably good agreement, and we can use that to understand what's going on in the system. Okay, I think at that point I have to stop. I'm anyway at the end. I showed you we had some method to make these fairly high Q nanocavities, and you can use them to probe some interesting exciton photophysics. I showed you this result with non-local coupling, and the last thing I showed you very quickly was this interlayer exciton coupling and the presence of nonlinearities when you pump strongly. I'd like to thank the people that did all the group at the beginning. If you want to see some publications, if you can, scan in and photograph that, but otherwise just send me an email and we can discuss it. Thanks so much for your attention.
Great. So thank you very much for being just on time. Very excellent talk. Also, I still have to allow at least one very short question. So is there any question in the audience? Okay, over there.
Very nice talk. So this nonlinearity that you showed, is that lasing or is that...
Yeah, so we called it lasing. We see line narrowing and we see a nonlinearity. I think you want to also look at the photon statistics and see a transition from a thermal state into Poissonian statistics. We're doing those experiments. The problem is the lifetimes are fairly short, and if you want to see a vanishing of a bunching at 0 time delay in Hanbury-Brown-Twiss experiments, you need very fast detectors. Luckily, we have now very fast detectors, and we're trying to confirm that. So I've called it lasing, so I have to stand by that, but I think tune in next time. It could be that I'm writing, it's no longer lasing, it's nonlinearities. Yeah.
And then would you consider it photon or polariton lasing?
I'm sorry, I didn't get it.
Would that be photon lasing or polariton lasing?
Well, this is then photon lasing. Okay. Yeah, we're not really in the strong coupling regime here. Okay.